All right, so we're going to talk about programming languages. And the thing that I need to start with, I think, that we all need to understand is computers don't understand programming languages, right? They need help to understand it. And that's why we have compilers, we have interpreters to actually take something that we can understand, which is our programming language, and make it into something the computer can understand. The only thing the computer can understand is zeros and ones, machine language. So we take whenever we're talking about a computer language, we have to translate it into machine language. Machine language is the only thing the computer can understand. So we take our very fancy computer languages, we translate them first, and we call that translation process, it's either interpreting or it's compiling. And we will talk about that during this course, I suppose. But the very simpler, so we had our simple programming languages going back in the history. They were just zeros and ones. So it was already machine language. So if you were a programmer, that's how you talk to the computer, zeros and ones. So you had to know what the zeros and ones meant. That was our first generation programming languages, machine language. Then we got something a little bit more usable. Second generation languages, we actually had some little commands, load, etc. Where's the thing? We had some very small commands that we used. That was assembler languages. So the assembler language would then have to be translated into machine language so the computer could use it. That was fine. We did that. Then we got our high-level languages, which is above the assembler language, where we're like a Grace Hopper, right? A COBOL programming language. These very, very wordy languages, big English words and stuff like that. So you could create something in a computer language that somebody else could read and sort of understand. They would still have to be a trained computer professional, but it wouldn't take 10 years to train them, right? Or, your average person could learn how to read that and sort of write that programming language. Then we got more recently our very high level programming languages where we're starting to do things with objects, and the objects have properties that apply to them. There's classes, there's methods. And so we're getting into our very high level programming languages like Python and Java, etc. So that's kind of been the evolution. As the programming languages have become more higher level, it's been easier for us as programmers to look at it and to understand it and work with it. But then the translation process has been a bigger job, I suppose. But that's fine because we have tools to do that. All right, so what about programming languages? Let's see. Here's an example of a recipe that you could give this to a person, and a person would be able to go and do it. Say, okay, here's a recipe, here's some ingredients, and here's some steps. That could be like a program. Yeah, okay. But if you could cook, you could do it. If you followed the instructions, you could get this right. But the thing about these instructions is you have to do the right thing at the right time with the right ingredients. Yeah. And so long as you follow the steps and do this first and then this after, you know what I mean, and follow it exactly and put the right ingredients, you'll get something that'll work out okay. And that's the same with your computer program. Not only do you have to do the things, but you have to do them in the right order at the right time with the right data. And so that's the analogy how that works. Is our recipe for a human is kind of like a program for a user. Now, the purpose of the next two slides, slide 3 and 4, there's a little bit there explaining it, but the purpose is to show that we can have a representation of the same thing happening, and we can show it two different ways. So here we're showing, basically it's the Excalibur story with a twist. Not a very nice twist, a kind of a very sad twist, I suppose. But we see that in pictures. You can look at those pictures and you know what it means, right? Dude finds sword in rock. Dude thinks, that sword, if I pull it out of the rock, that's going to be good for me. I'm going to be like king, right? When he pulls, he trips, sword impales him. So it's not great. It's not Excalibur. It just looks like Excalibur. Very good point. So the problem is the guy didn't check it out. He thought he had Excalibur, but he had a sort of a fake Excalibur. And we have a story that sort of explains it. And so the point being that this thing here and this thing here basically tell the same story. The story can be shown in more than one way. Now, algorithms can also be shown in more than one way. So what is an algorithm? Algorithm is going to be step-by-step explanation as how to solve a problem. A problem that could be solved by a computer would be an algorithm. And so, as the notes say, we've got lots of different ways of explaining the same thing. That story about Excalibur, I could write something for you in English. There was something was written in English. I could speak it to you. Somebody else could speak it in Arabic, all right, or some other language. And people that understood that would work for them. I mean, so there's more. It would still be the same story, right? Just with different words. And but the meaning could still be the same. Well, it's the same with algorithms. With algorithms, we can have a problem and a solution, and we can explain it in different ways. We can use plain English, which is just like a story. You know, this is what I think you can do to solve this problem, kind of thing. Or we can use something a little bit more structured. And in fact, this thing here, it's not the pseudo, by the way. The P is silent. So you just say pseudo. Pseudocode. Pseudo kind of means almost the same as, but not quite. Yeah, so pseudo is almost the same. So almost the same as code, but not quite. So pseudocode looks like code, except, and what I was going to say is, we used to call it structured English, because it was kind of structured English. If you look at pseudocode, it just looks like some English-speaking person sat down and wrote things in a very structured way on how to solve the problem. And it is very structured. It's not just sort of rambling English. We have a structure to it. We have a beginning and we have an end, and we have a way of saying everything. We use indents to represent that this thing is part of that thing, that type of thing. So pseudocode is very useful. A flow chart is just like the diagram that we used for the fake Excalibur. We can have a diagram to show us what we're going to do, and we have special symbols for that as well. So our algorithm, so let's see, here's two ways of showing how to solve a problem. Now, it's the same problem with the same solution, but the representation is different. We got pseudocode, which must have a beginning and an end. We have indents of everything that happens within this thing here. So basically, we just got some instructions, a bit about input, some process, and another process there, and then an end. You know what? We missed the print here. There we go. I thought that was funny. All right, so we have some special symbols in the pseudocode. This is pseudocode. In the flowchart, we have some special symbols. If it's got rounded edges, then that means it's a connector or a start or an end. Connectors are used to join pages. But start and end must have rounded edges. These things with the sharp edges, right? It's a parallelogram that is not a rectangle, whatever you call it. So these things are inputs and outputs. And quadrilateral. Yeah, all right. So, and then the one that's a proper rectangle, that's a process. So a process is where something is done. Input, output, we just get something. So I hope that means it's easy for you to sort of see this and understand what it's doing, because each of the symbols has a meaning. So that's kind of why we use it, I guess.
The diamond is division, right?
Yes, and there's no diamond in this diagram, but diamond is a very important part of a flow chart, and it is a decision because a diamond is going to have more than one arrow going out of it. So these should be arrows. The lines that connect one part of the flow chart to the other should be an arrow, and when you have a decision, you represent that by a diamond and one input and two outputs, depending on whether it's true or false. So the diamond is going to have a decision, but the decision is going to be like an if statement or something like that.
You know the shape of the box or whatever it matters?
Yeah, it does. Yeah, the shape of the box is the symbol. So the rectangle means that that's a process. It's doing something. The parallelogram with a non-rectangle, that just means it's input or output. The rounded edges means that it's the start or the end. And as mentioned, the diamond means that you've got a decision. All right, so we have this other thing called, computer can't work on an algorithm. Computer needs machine code. And so we, as programmer type people, IT people, we're going to take that algorithm and we're going to make a program. Then the program is going to be processed using some kind of a compiler or an interpreter into machine code so that the computer can actually do something with it. So we have program code, and program code is going to be specific to the language that we use. Now, the other thing is, depending on what level of program you're using, if remember we had level 1, which is machine code, then we have level 2, which is your assembler level or assembly level. Level 3 is high level language. Level 4 is your very high level language. If you're programming at machine code, the program that you write at machine code on your Apple computer is not going to work on your IBM computer, on your Microsoft computer, right? Are you with me? And the one that you write for your iPhone is not going to work on your Android phone. So they're different. The hardware is different. It needs different machine code to work on it. You'll know that because if you go to download an app onto your iPhone and you get something from the Google store, it's not going to work, is it? You have to go to the Apple store. And likewise, if you're using your Android device, you need to go to the Google store. You can't go to the thing at the iPhone store is not going to help you at all, right? It's actually the processors are different, and so the programming is going to be different. Now, when I say the programming is going to be different, in each case, that processor is going to use machine code. But we're going to take our programs and we're going to convert them differently to work on the different machines. So you could have a programmer who would write a program in Python or in C, and it will work on both an iPhone and. But what the reason is because they're going to compile it differently. They're going to compile it over here so it works on the Android. They're going to compile it over here so that it works on the Android, and the actual result will be different. Don't mix them up because this one will only work on the iPhone. This one will only work on the Android, right? Because of different processors. So I hope that makes sense. Now, I think enough on that. We've got two different ways of getting to that machine code from our program code. We can do it by interpreting, or we can do it by compiling. Now, interpreting, what it's going to do is it's going to take the program one line at a time. As that line comes in, it's going to process it, then go to the next line. And so with interpreted code, it's going to be open and anybody's going to be able to see it. If you distribute your interpreted code, they're going to be able to see it, which means they can change it. So that's less than ideal if you were going to have any security in your device. So what people tend to do, if they're distributing software to people around the world kind of thing, anybody can have it. What they're going to do is they're going to compile it. And then they won't distribute the code itself. All they distribute is the compiled code, which is just machine language. And anybody can open that up. Those files are visible. You can open them up, and what you'll see inside is just a bunch of zeros and ones, which is not going to mean anything to hardly anybody. And so that's the idea. So, for example, you've got distributed on your computer lots of programs, but let's say all the Microsoft programs. They're going to be a lot of DLL files and some .com files and some .exe files. Those files, if you go to look at them, you can look at them. You can open them up with the text editor. It's just going to be a bunch of zeros and ones. I mean, there's nothing you can do with it. That's the way they want it. They don't want you to mess it. Now, on the other hand, if you are a Linux person, you can download from the internet the Linux, and they'll give you the source code. They'll give you the compiled code so you can run it. But if you want, they'll also give you the source code. You can so the idea there is you can have your own sort of, how do you say, customized operating system for a particular device or a particular application. But Microsoft's not going to give you that. And a couple of reasons, right? So one, obviously, there's a commercial reason they're not going to give it to you because they don't want you to steal all their stuff. I mean, they've got very high paid programmers that they pay to develop this stuff. They're not just going to give it away. So there's that. But the other thing is, if you start messing with it, right, we're going to end up with 5,000 different versions of Microsoft out there. They're not going to be able to control it. They're not going to be able to support it. And now you might say, so why does Linux do that? Well, Linux supports what they've got on their site, which is a open source. There's a community of people that support that. So they're checking it. If you make a change, they're checking it. Kind of like Wikipedia or kind of thing, right? So that's understood and it's accepted. Oh my gosh. So here's a little bit of a plug, I guess you'd say, for Python. So it might be the first programming language you've seen, it might not. But when you look at it compared to other programming languages that are high-level programming languages, you might look at it and say, well, that's an easy language. That's just a toy language. It's not a toy language, right? It's the real deal. There's a lot of things that you can do with Python. You can get in and sort of manipulate around and find out things about your operating system. You can organize and program your routers and your switches on your networks. It's a very powerful program. It just looks basic. And maybe that's the magic of Python. I mean, it's easy to get started, but there's a lot of things that you can do. Now, with these very high-level programming languages, a lot of what you can do is determined by the libraries that come with them. What libraries do we have available with them? And so that's definitely true for Python. There's a lot of new libraries. So when I say that you can get in there and you've got some tools, some kits that you can go and manipulate the operating system, that's because somebody wrote those libraries. That wasn't the case when Python was new. So Python's been around for a while and starting to get these libraries that are very useful. Another example of that would be like, for example, JavaScript. JavaScript and jQuery, these kind of programming languages, what do we use those for? They're only used for writing web pages, but they're used for writing very dynamic and very useful web pages. And there's a lot of libraries that sort of go with them. You can do a lot of things with web pages with them. Now, the thing about the libraries, they can make programming a lot easier for you. All right, so you find these libraries and they'll do really things that seem to be really engineering tough things. And they can, so find the right library, you plug them in, and you find it, your website or whatever it is you're programming will do a lot of things for you really quickly, really nicely. So the libraries have been sort of perfected by computer professionals. So I think that's maybe the exciting thing about programming in the year 2022 that you're going to find. Every year here we have a capstone project, which the graduating students, who have finished their software development program, they'll do it. The hardware students also do. But the hardware students is building some network that does some wonderful things. But the software students, they'll develop some system. And this every year they just get better. I mean, I see these systems that they got and it just blows me away. I mean, they're doing these wonderful things. And what it is they got 10 students working together on a project, but they produce something which is really top class, right? Really sort of would work in a business environment, would be accepted in there. But a lot of what they've done is they've been able to find libraries that will do some special things for them. And we just get these really slick, really professional sort of systems that work really well. So that's what they're capable of. That's what you're going to be capable of in a couple of years' time. So exciting times for you lot. So yeah, the low-level languages, I think I've explained that to you, that low-level languages are going to be specific to a particular program, computer, to a particular computer. The low-level language, machine language that you wrote for your Apple is not going to work on your Microsoft machine. Okay, so we've got some other programming languages that there's many there that we can talk about. Hopefully you'll learn about that. More recent procedural programming, that's kind of cool. Procedural programming is your third generation programming language. More recently is, we've gone past procedural programming. Procedural programming is very 1960s, 70s, 80s. That's basically the way you're going to learn how to do Python programming in your first couple of semesters will be procedural programming. In your third or fourth semester with Python, you'll start using the object-oriented aspects of it. So that's kind of more modern and much more powerful. So, I mean, here's what I mean by, so you can create an object and then you can have a sort of a button related to that object and sort of just click on it and a whole new sort of bunch of programs and activities happens. You can do that with that object-oriented language, which you couldn't do with sort of like C or Pascal very easily.
You slides. You skipped slide 8 because I don't understand anything that.
Which one's slide 8?
The one. No. Go back. Another one. This one. I don't understand this code.
I'm sorry that I missed that. Okay, let's look at this one because it seems I skipped it. All right, so the first level here, this is our machine code. So machine code is just zeros and ones. The computer understands this. The computer understands this. And so if you were an expert in machine code, you would write something like this, and it might tell the computer to do something like this. The computer would actually do something like take two numbers and add them together, but you'd have to write these 8-10 lines of code to get it to do that. So basically all of these are kind of doing the same thing. Putting two numbers into memory and adding them together to get something. But this is how you do it in machine code. Now this is the same program as that. The only difference is here, we've converted the binary code into hexadecimal. And so it just takes up less space. That's all right, in our representation of it. So this number is the same as that number. This number here is the same as this number, right? So basically we're just doing that, okay? For example, do you notice these strange things here, right? So 2004, I mean, it's not the number 2004, it's a hexadecimal number 2004. FFFE, okay, hexadecimal numbers go from 0 to F, which is 15. Yeah, instead of saying 15, we say F. And so instead of saying 14, we say E. And so, yeah, so it's these numbers are those numbers. Okay, so I'll show you how to do the conversion on that in our tutorial. So tutorial is we're going to do this to this and this to this. So that's our tutorial. Now the next level down is our first generation languages. Our second generation languages here, we got some symbolic code. And basically the symbolic code is just saying, well, we can load things into a memory location. We can add two things together, that type of thing. So we've got some simple instructions that we can do here. Now this has, remember the computer can't work with this. This has to be converted to this. So that's what will happen is you'll take your symbolic code and you'll convert it to this. Here's another way of looking at that symbolic code. Or these are the meanings of some of the symbols that are there, right? And it's an explanation of them there. So we have some symbols that we can use. ORG. So second generation language is kind of compact, but still has to be converted into machine language before the computer can understand it. So we take this and we convert it into that. Our third generation language is going to be much more human readable. Okay, so this, I mean, you look at that like, what? You know, 000, what the LDA? Come on. What's that? But this might make a little bit more sense. Integer A takes a value of 83. Integer B takes a value of 23. And integer C. So what this is saying is create three variables. So when you create three variables, what you do is you set aside three memory positions in the memory. And you say, okay, this one is going to be A, and this one's going to be B, and this one's going to be C, and A is going to have this value, and B is going to have this value. And they're all going to be a special type. They're all going to be integers. So in programming language, that's C. In C programming language, we have to type the variable. We have to specify, we have to explicitly type the variable. We have to say that this variable is type integer. And if you try and put another type of value in there, you're going to get a big error. Right? So if you say, oh, this is an integer character in there, you know, it won't work. Or if you say this is an integer and you try and put a float value in, a float value is like a decimal number, that's going to no fraction. It's not going to work.
Yeah. In C it says A plus B, but on the box it says 0, like C. Question C, it says 0, but they're saying A plus B, and A plus B doesn't equal to 0.
C is equal to A plus B.
Yes.
C, now it doesn't mean C is equal to it. C says C takes the value of A plus B. So an equal like this doesn't mean equal like in math. It means takes the value or is assigned the value. So I don't know what you mean by the 0. I don't see
Look,
a 0
it's 83.
Up here?
Yeah, 83.
Yeah, right. Okay.
Plus or minus 23 doesn't equal to 0. So
No,
it
it doesn't.
says 0 on.
Yeah, I don't see the 0, but yeah, A has a value. A takes a value of 83. B takes a value of minus 23. C takes a value of whatever A and B are. It's not going to be 0. You're right.
No, because look, 83 minus 23, and under it there is 0.
Okay.
Yeah.
All right. Yes.
Yes.
That's because we haven't done the second step yet. That's before we did, we're only here. Okay. So here C is 0. Then we do the next step and then yeah.
Oh, okay.
Sorry, sorry if it was confusing. It hasn't done the next step yet. But good that you picked up on that. So, I mean, that's very good that your attention to detail. It's very good for computing. Is that you look there and you notice, oh, that something's different. That's really, really good thing to do when you're looking at computer programs. Why is that 0 there? Yeah, good. But the reason it's there is because we initialize it. When we initialize it, it'll take a value of 0 or null. In this case, it seems to be 0. Now, I do want to make that point about the assignment. The equal sign here is not like a mathematical equal. It's not saying that, these two things equal that two things. It's not equality. What it means is whatever's on the right is going to be assigned to this variable. This variable is now going to store whatever was in the right. So A is a variable. And I hope that makes sense. So what I want to say is, so we had this level. When we get down to this level, we write this. Then we have to convert this to this. It still has to be, the computer is only going to work with this. So we have to have some way of taking this and making it that. And so we're going to have a compiler or an interpreter that's going to do that for us. It's going to take our high level language and convert it back into machine code, because this is the only thing that the computer can understand. And so we have these nice programming languages that are tools that we can use, so we don't have to write this stuff. We can write something simple, right? So somebody's gone to a lot of trouble to write this compiler and editor so that we can get this. Does that make sense?
Yes.
All right, so that's what we've done. And I'm really tired. I don't know about you guys. Yeah, the next stuff is notes on 3. I think did I get?
Yes.
Did I skip any of this other stuff?
You didn't do high-level language.
I didn't talk about this, but it was in that slide. So we see a hierarchy here, or things on top of each other. So we have this hardware at the hardware level. Then we have machine code. Machine code is those 0s and 1s. Yeah. And then the assembly language is the level above that. So here's our Python. We're taking our Python. We don't have to get down to the hardware level. We don't have to do that. All we have to do is get to the machine code level. When we do compiling, it's going to get to the machine code level. Assembly language also has to get to the machine code level. The computer can only understand machine code. All right, so that's cool. And okay, so then the last slide is just a bunch of symbols which represent computer languages that you might come across. So definitely come across Python. We're going to be doing that soon. JavaScript, when you might have if you guys are in the programming strand, you'll have a couple of semesters of Python, then you're going to have a bunch of semesters on JavaScript. And in your 3rd or 4th year of that, you'll be doing PHP, because you need PHP in order to connect your website to a database. So a website without a database, what's the point of that, right? So we used, if you're going to have a proper website, you probably want to have a database with it. So you can use PHP. JavaScript, sorry, Java, not JavaScript. Java is kind of older than Python. Probably Python can do just about everything that Java did. But, you can embed Java or Python code into a website. So I'm talking a lot about websites, right? Websites or app development. That's probably where you're going to end up doing a lot of your programming. So you could be using Python or Java in that.
So is Java old?
It's a little bit old, 1990, that kind of thing. Does that seem old?
No, because there's a cafe called Java too.
Yeah, that's right. C++ and Python and Java are all object-oriented languages. Now, I think R and Ruby on Rails are used for data science, for big data, for artificial intelligence. So if you do that strand, you'll probably come across them. So you'll be creating big databases and running these programs over them to find patterns. That's what I think. And I'm going to say that I'm kind of done there. Okay. So